Alright. Okay. From this week onwards, we have here now we are at week 6. So for week 6, 7 and 8, we are going to discuss about angular kinematics. Talk ni sebenarnya kita dah bincang. Talk ni kita dah bincang secara asas dekat topik equilibrium. This one. Okay, dekat topik ni kita dah bincangkan pasal torque. However, we are going to do some revision on it regarding torques and equilibrium, and later on we are going to continue with angular kinematics. Angular kinematics ni kalau tengok dia tak banyak tapi agak memeningkan kepala, so I'm going to go quite slow on that. Alright, and then this week we are going to have your first quiz. It will be conducted on Thursday evening. Okay, chapter adalah sehingga apa yang kita belajar sebelum cuti lah. It will be up until work, power and energy. Most of it is going to be an objective quiz. If I'm not mistaken, there will be 10 objective question only, and it will be conducted in 1 hour. Okay, hari Khamis. Okay, ada soalan sebelum kita mulakan topik hari ni?
Tak ada, sir.
Alright. Sorry, sekejap Okay, so kita akan revise a bit about torque. Okay, kat sini ni lah. Kita dah belajar masa equilibrium. Okay, torque, bila kamu nampak torque ni, when you see this term, this is actually force. Okay, it is actually a force which being subjected to any object and it cause rotation. Okay, it cause rotation. So torque is a rotary effect. Rotary effect ni putaran lah. Okay, rotary effect of a force about an axis of rotation. And when we talk about torque, we are going to have two things. First force, second is moment arm of the force. Ni dua benda. Kalau kamu masih ingat lah, okay. I hope that you still remember this one. Okay, if we have an object, let's say a book, and we push a book, we put force to the book, it causes the book to move. Ni Newton's second law. Okay, this kind of movement is known as translation. Okay, ni type of movement. Jangan terlupa pula ni lah. Siapa buang masuk tu? Okay, it is known as translation, atau nama kampung for this translation is linear motion. Okay, linear motion. And if the motion is in one straight line, this is called a rectilinear. Okay, if we have a book and we apply force like this, not in the middle of it, it causes the book to move like that. Still in a straight line, but curved. This is known as curvilinear. Okay. However, if we have a book and we apply force like this, it will cause the books to rotate. Bila kita bagi force dalam dua arah bertentangan, it will cause the book to rotate. Okay, this rotation is known as torque. Okay, itu yang pertama. Yang kedua, when we push books, okay, and it rotate, it need to have an axis of rotation. Oh, apa tu? Siapa angkat tangan ke apa?
Sorry, sir. Tadi Irfan tekan, sir.
Okay. Selalu dia kalau bukan angkat tangan, dia message saya baca. Sorry Okay. So you need to have axis of rotation. Baru dia akan berputar. And then, okay, like I said earlier, when we discuss about torque, there will be two things. Okay, two properties play major role in torques. One is force applied. Number two, okay, some books you are going to see the name radius. Some other you are going to see moment arm. These two things is equal. Okay, these two things is equal. So kalau macam yang ini, Ini ialah putaran yang akan terjadi. This is the rotation that going to happen. Okay, so if we do an imaginary line like this, imaginary line of force and imaginary line of axis of rotation. Okay, this one, the line that connecting line of force and line of axis of rotation, this is known as force, moment, arm. Okay, it is force, moment, arm, which is perpendicular. Okay, force moment arm is perpendicular with force line or line of force and the axis of rotation. So this is force moment arm. So sometimes you see this term. Sometimes it is known as radius. Okay, radius. Some other time it is just known as distance. Okay, so kamu kena faham distance ni is force moment arm. Okay, where it force moment arm ni kan, kamu kena faham macam ni. Kalau force kita bagi macam ni, this is line of force. Okay, this is line of force, and then axis of rotation is here. So this is force moment arm. Force moment arm. Contoh macam kita tengok pintu. Okay, kita ada bilah pintu. Okay, ni dia punya bukaan pintu lah. And then somebody push from here, which cause the door to close. Hinges ni is the axis. Jadi force moment arm is between the force application and axis of rotation. This is force moment arm. Force moment arm ataupun dia punya distance. Kadang-kadang kita nampak benda macam ni. Ni bukan T tapi dia tunjuk jarak. Okay, kalau macam kita punya bicep. Okay, this is the axis of rotation. And this is your bicep attached here. So this is line of force. So between line of force to axis of rotation, this is force arm ataupun distance yang kita cari itu. So torque, the formula to find torque is T capital bukan koma sama dengan, okay, capital T equals to F D. Okay, distance. This is moment arm. This is force. This is how you find torque. Okay, ni datang ni. Ni datang nota, ni datang ni. Sekejap ni. Okay, so force, moment arm or the distance is between the application of force and the axis of rotation. That is the moment arm, force moment arm or the distance. Distance apa? Distance kat formula ni. Misal bila kita nak cerita torque equal, pelan mengarut ejaan ni. Torque equals to force and distance. This is moment arm. Okay. So some other books, saya tengok beberapa contoh formula how I want to make it larger. Okay. Some other books, bila kita cerita tentang torque, dia akan keluarkan formula F R ataupun macam ni, FR. Okay. So these are representing radius. Or ini sama je dia distance. Radius of what? Radius between force to axis of rotation. Kalau force dia bagi tegak, senang tegak. Tapi dia bila jadi confusing bila force being applied macam ni. Okay, bila force being applied macam ni, meaning you need to draw one other imaginary line perpendicular, bertentangan, okay, with the force line, and connecting that line, axis of rotation, to the force. This is dia punya R, ataupun dia punya D, ataupun dia punya force moment arm. Kamu kena ada dua benda ni. You need moment arm, you need force, and then only we can calculate berapa torque you are going to have on the system. Okay, ini asas dia. Alright? This is what torques it's all about. Okay, saya bagi satu contoh lagi. Kita ada buku tadi. Kita ambil buku. We apply force. Okay, we apply force. Alright. If the case like this, you know that this going to rotate. Okay, it's going to rotate. Dekat mana moment arm? Radius dia is not this one. This is not the radius. Okay, that is not the radius. But the radius will be, since we know the force line is in a one straight line here. Okay, this is a force line. So you need to imagine one other line perpendicular to the force line intersect with the axis of rotation. Jadi berapa dia punya radius? This is the moment arm. Okay. The distance between these two perpendicular line is the moment arm. Ataupun dia punya distance, ataupun dia punya radius. Sama je tiga natang ni bila kita cerita tentang torque. These three things representing the second part of the equation of torque. This is the length. Okay, this is the length. Right, itu asas. Okay, number 2. When we talk about torque, our body, when we try to maintain equilibrium, meaning that the summation of torques in our body need to be 0. Need to be 0. Okay, need to be 0. Example, bila kita ada bicep curl. Okay, this is the resistance. This is the force. So resistance work this way, force work that way. Kamu dapat bayangkan this is a torque. Torque tadi buku, kita ada satu force dan dua force bergerak pada arah bertentangan, which cause the books to rotate. Same here. By having these two directional force, it will cause our hand to flex and extend. This is torque. Okay, this is what torque looks like. Okay. Alright. So now, we know that in the concept of equilibrium, okay, equilibrium, at any given point of time, force horizontal equals to 0, force vertical equals to 0, and torque also equals to 0. In other words, in order to be equilibrium, the summation of torque kena jadi kosong. Okay, two concept. And now, what is the summation of torque? Can you see these two complex? Complex of force, complex of resistance. Okay? And like I said earlier, when we talk about torque, it is force time with distance. So now here we have the elbow as the axis of rotation. Itu yang pertama. Jadi kalau ini force, okay, this is the line of force. This is the axis of rotation. Moment arm dia dekat mana? Force moment arm. Where does force moment arm located? Come on guys, kat mana?
Yang horizontal tu.
Horizontal. Okay, dekat mana ke mana? Daripada axis sehingga?
Anti-resisting.
Bukan. Force apa yang dekat force je lah.
Force.
This is force moment. Yang kamu kata tadi tu daripada axis sampai resistance, this is known as resistance moment arm. Daripada punca resistance, which is here, okay, in the middle of that, towards axis of rotation is resistance moment arm. Sebentar ya. Okay, sorry. So, kita sambung. Okay. Alright. So, we know that in order to have torque, kita kena ada force and distance. And in torque, we have two different force acting from different direction. Okay, force 1, force 2. Jadi, resistance ni pun memang torque. Kamu jangan confuse kenapa resistance jadi force. Okay, resistance is actually weight. Weight is mass times gravity, resulting a figures in Newton. Figures in Newton is force. So weight is also a force. Jadi kita ada satu force, I name it as force 1, and we have this is as force 2. Okay, dapat bayangkan ini. Can you see this thing?
Dapat sih.
Okay, now we know that in the concept of equilibrium, net torque, okay, net torque is zero. What is the meaning of net torque? Meaning, combination of all torque in the system come out zero. Okay, so in order to this system to be stabilized, it can be written as this one. Torque equals to, okay, it will be FME plus RME. Okay, and this equation need to be zero. Baru dia balance. Okay, so saya bagi satu example. Let's say we have a dumbbell. We have a dumbbell. Let's say 20 Newton of dumbbell. Okay, we have 20 Newton of dumbbell. Okay, and RMA berapa panjang tangan kita ni? 38 cm lah lebih kurang. 38 cm, and for FMA this one is roughly around 0.8. Susah lah kita ambil nombor senang je. Ambil satu je lah. 1 cm. 1 cm. So, how much force needed in order to stabilize the system? Kita tak tahu force. Enggak tahu. Okay. FME 1 cm. RMA 38 cm. R 20 Newton. So, how much F? Ni selalu perkadaran. This is some sort of common question in order to understand torque. Okay, jadi apa yang kita akan buat? So we are going to see something like this. Summation of torque in the system need to be zero, and this zero equals to force 1 cm ni kita kena tukar jadi meter dulu, pasal dia punya formula, dia punya rumus is in Newton meter. So it will be 0.01 plus, okay, force here, positive ke negative for the resistance? Is it positive or is it negative? Force bergerak ke atas.
Positive.
Negative. Okay, ingat yang tu. Negative 20 times 0.38. So based on this, you can find out F. Jadi F ialah berapa ni? Tolak 20 0.38 bagi dengan 0.01. So how much you get for F? Times 0.38 bagi 0.01. Kita dapat sini 760 Newton. Betul tak? Betul 760. Okay.
Betul sir.
Alright. Why 760? Okay, now look. If F equals to 760, FME equals to 0.01, R equals to -20, and RME equals to 0.38. Sekarang kita masukkan dalam equation summation of torque. 760 0.01 plus 20 0.38. Look, this is the reason why. So we end up with 0. In other words, this part equalize with this part. Part positive ni equal in term of magnitude with the part negative, which resulting no movement at the system. Bila no movement, meaning equilibrium. So this is what equilibrium play major roles in torque. Okay, in torque. So kalau kita dapat bahagian positif ni lagi banyak daripada bahagian negatif, we are going to get flexion. If we get negative is larger than positive, we are going to get extension, movement. This is torque. Okay, this is torque.
Boleh tak saya nak tengok yang di sebelah tadi?
Ini, tadi. Settle bagi tahu
Yang next pula.
Next page.
Okay dah.
Alright. So I give another example for you. Try to find out the question, the answer. Okay, let's say we have a case. We have a case of pushing a door, just a normal case. Okay, this is the axis. This is the door. Okay, and somebody, okay, let's say A push the door here. Okay, it pushed the door here with a force of 200 Newton. Okay, and the force arm for A, force arm for A is 60 centimeter. Okay. At the same time, there are somebody pushing from B with force arm of B at 48 centimeter. Okay. So the question is, how much force applied by B in order to make this system equilibrium? Means that the door does not move. Berapa banyak F pada B? So, tips. It is the same. You need to find the total torque of this system, which is comprising of torque A plus torque B, ataupun FD A plus FD B. And again, in biomechanics, okay, in biomechanics, in physics, direction give meanings. Jangan lupa yang itu. Jadi kalau kata direction give meaning, automatically this part is going to be positive ke negative?
Negatif.
Negative. Can we put this part as negative, this part as positive? Can we do that?
Tak boleh sir.
Boleh. Jawapannya boleh. Kenapa boleh? Simple je. Pasal negatif dengan positif ni just to show direction of action. Okay. Boleh. Ini kalau kamu tengok pada atas. Tapi kalau kata kamu tengok pada tepi, satu tolak ke sana, satu tolak ke sini, kan jadi lain. So, as rule of thumb, okay, as rule of thumb paling pada saya mudah je lah. Just follow balik Cartesian. Benda ke bawah semua negatif, ke atas semua positif. Apa benda ke kiri semua negatif, ke kanan semua positif. Just follow that. So kadang-kadang bila kamu buat soalan, baca-baca buku kan, kenapa dia ni terbalik lah? Reason is, as long as the direction being shown, it's okay. Tapi kalau tak nak sakit kepala, pegang satu je. Goes downward, negative. Okay, silakan. So I name it, saya keluarkan formula, saya keluarkan maklumat. We have FA equals to negative 200 Newton. Moment arm, okay, I put it as DA, 0.6 meter. FB, we don't know it yet. And B is 0.48 meter. So please find out FB.
So jangan 120 tu macam ni boleh dapat 120?
Ni?
See, 250 sir.
Betul. Ni kali kan? 200 kali 0.6, betul jawapan dia. Kalikan ni dulu, baru dapat yang atas ni. Sekejap saya tulis yang besar ni. Kita kurangkan kekeliruan. Jawapan kamu betul, 250 Newton. Okay, macam mana dia dapat? Right, so this part, we send it to left hand side. Jadi akan jadi,
Dah dapat.
ha?
Dah dapat.
Okay, it's okay. sama dengan 200 kali 0.6. Dapatlah yang tadi. And then, kita nak X sahaja. So, this part, we send it down there. 0.48. We end up dengan 250. So, X is 250 Newton. Means, force B is 250 Newton positive. Meaning that there are another force acted in vice versa direction compared to A. And this force equalize the system. So, pintu enggak akan ada pergerakan. Itu dia, equilibrium. Okay, saya bagi satu contoh lagi. Contoh equilibrium dalam bentuk yang berbeza. Yang ini dia ada macam sedikit mengelirukan. But let's try it. Okay, this is yang ni settle belum? Kalau dah settle saya proceed. Kalau belum saya tunggu dulu. Just let me know when you settle. Dah Okay.
Yes.
Alright. So this next
Yang kan F untuk B kan is 280 Newton kan?
250.
Oh, saya tulis salah.
Alah, saya tulis bersambung je. Kamu
Okay.
janganlah gitu.
Okay, so
Okay, my bad. Tulisan buruk macam ayam. Alright.
So, kenapa dia jadi equilibrium? Because of force dia lain. Faham tak maksud?
Okay, faham? Tengok sini kan jarak dia jauh. 60. Sini kan jarak dia dekat. 48. Okay, kenapa dia jadi equilibrium? We know that bila equilibrium, torque dia kosong kan? Masuk kosong ni, kalau kita bagi satu benda, kita tolak sini, there is no movement. Dia tak bergerak macam ni, dia pun tak bergerak macam ni. Dia static. Maksudnya those two force equalize the system. Okay. Kita ambil yang tadi. Force A dengan distance A. Force A ialah berapa? 300 200 dengan distance A 60 cm. Okay, force B equals to 250. Distance B equals to 48 cm. Okay. If these two system is equalized, figures akhir dia, torque A akan dapat sama dengan torque B. Okay. Now let's find out. Torque A equals to FA times DA equals to 200 times 0.6 in meter. Okay. So you have it 120 Newton meter. Betul tak? Pun kadang-kadang salah ke buat benda ni. Inilah kira. Yeah. Torque B equals to FB times with distance of B 250 times 0.48. Meaning here, Newton meter. Pintu ni, there are 120 Newton per meter works on this side. Try to push the door like that. And at the same time, there are 120 Newton meter works on the other side to push the door that way. Since the force ni, Newton meter ni, okay, since the amount of force being applied is equal, bergerak tak pintu ni?
Tak, sir.
Tak. This is what we call equilibrium. Sama lah dengan tangan tadi. Kan tangan tu, kita nak contract ataupun kita nak lengthening. These two, kalau contract, meaning that bahagian force lagi banyak daripada bahagian resistance. Tapi kalau resistance lagi banyak daripada force, tangan kita akan retract. Since there are no movement, meaning this is in equilibrium state where force here is equal with the amount of resistance, causing no torque. Kadang kita susah torque. No rotation occurs. Torque is actually a rotation in angular motion. Rotation ni bila kita sebut linear. Tu dia. This is why it is called an equilibrium, because those two states is actually equal in term of magnitude. Ni magnitude lah, berapa besar in term of magnitude. Jadi kalau kata dekat sini 100 Newton meter and at the bottom is this one is negative 100, this one is positive 110 Newton meter. Dia bergerak tak? If this is the case, are you going to see movement? Kalau kata case ini, 110 Newton push from here, 100
Yes.
Newton, yes, dia akan bergerak ke mana? Ke atas ke ke bawah?
Ke atas.
Ke atas. Jadi dia equal ke tak equal? Equilibrium ke tak?
Tak.
Kenapa dia tak equilibrium?
Because this is not equal. Newton meter tak equal.
The figures is not equal and there are movement. Bila ada movement, ada benda nama dia velocity. What cause velocity? Apa yang menyebabkan adanya pergerakan? Adanya acceleration. And as what we have learned during our early classes, when we have acceleration, acceleration disrupting equilibrium. Acceleration disrupting inertia. Bila dua benda ni tak ada, there is no equilibrium. There is changes. Bila tak ada acceleration, there are no changes. Maksudnya velocity dia kosong. Bila velocity kosong, there are no movement. Kalau pintu, static, tak bergerak. Kalau orang, berhenti, tak bergerak. Anything does not move because dalam sistem yang equilibrium, ada force tak? Jangan sakit kepala. Patah balik belakang ni. Ada force tak? Is there any force in this system?
No.
Habis ni apa?
Oh, ada. Kiranya
Ada,
maksudnya
tapi
kalau
dia
equilibrium.
dia equal. Dia sama. Which causing there is no movement. Bila tidak bergerak, tidak semestinya tidak ada force. There are force. But the force is equal, resulting no movement either linearly or rotationally. Top. Samalah dengan yang ni tadi. Mana tangan tadi, tangan kita. Ni tangan ni. So kita prove dah. Force 7.6 Newton. Resistance also 7.6 Newton. Since dia sama, there won't be any contraction. There won't be any apa ni? Extension. There won't be any flex. There won't be any extend. Pasal apa? Pasal bila dia nak flex, bila dia nak flex, force sama je banyak dengan resistance. Bila dia nak extend pula, resistance sama je banyak dengan force. So dia tak boleh tarik tangan kita ke bawah dan at the same time our bicep cannot curl our hand upwards. So it stays static. That is equilibrium in term of torque. Okay. Okay, saya nak tunjuk satu lagi konsep torque. But this one is much towards what we call it center of gravity. Okay, kita cerita torque dalam center of gravity. Now, let's say we have kan kena kutuk lagi dengan kamu. Apa rasa ni? Tadi tulis tak lawa, sekarang lain pula sini. Kau bayang ke jalan lain ni tegak? Okay, katalah kita ada satu axis of rotation. Okay, kita ada satu axis. Okay, this is 1. Ni jarak 2, 3, 4, 5. 1, 2, 3, 4, 5. The numbers representing distance from axis of rotation. Okay. Now, alright, let's see. I put an object here. Okay, I put an object here. And let's imagine, okay, weight dia ni, dia punya berat kat sini is 1 penny. Sekeping duit shilling. Okay, and then I put another penny. Okay, I put another penny dekat sini. 1 penny. Alright. Now my question. Is this system equal? Dia boleh berdiri tegak ke dia tumbang ke satu arah?
Tumbang.
Tumbang. Okay, my next question. How to make it equal? Ni center of gravity. How to make it equal? Macam mana? Macam mana kita nak buat ini? Macam mana? Okay. Jadi kita tahu, okay, this is the concept. There will be movement like this, betul? Adakah kamu bayangkan pergerakan dia seperti ini? Tombang satu naik, betul? Tolong cakap betul. Please.
Betul.
Betul.
So, bila dia betul, maksudnya this is a concept of torque. In order to balance things up. Ni sama dengan konsep badan kita tadi. So, one force acted here, one force acted here. Two force acted from different direction. Cause torque. You know that you need to add up something dekat sini. Okay, that is you know that there's going to be. Okay, you need to put something there in order to balance things up. Okay, to balance things up. Now, my question is, where should you put another penny in order to make this system equilibrium? Dekat mana kita nak letak? Ni ada konsep force arm,
Right kot.
movement arm. Memang dekat sebelah right. I know that it will be at this point lah. Dekat mana-mana dekat sini. Soalan dia dekat mana? Dekat 1 ke, dekat 2 ke, dekat 3 ke, dekat 4 ke, dekat 5? Put another penny. Meaning at the end of the day, this one will have 1 penny, this one will have 2 penny. Dah bagi clue dah ni. In order to make things equal. But the question is, where? Silakan jawab soalan itu. Okay, saya bagi clue. To make things equal, okay, to make things equal, kita kena ada summation of torque. Summation of torque, kita boleh dapat dengan summation of all those in system. Ni summation. All those in system. Okay. So, boleh tak kita cari dulu berapa torque kita ada dekat sebelah sini? Berapa torque kita ada? Equals to, okay, this is this penny. Pergerakan penny ni dia ke mana? Secara lumrahnya, dia akan menyebabkan berat tu bergerak ke bawah lah kan?
Bawah.
Jadi, force dia, kita tak ada value. So, kita akan namakan dia sebagai 1 penny. Distance dia berapa?
5.
5. Is it only 5?
-5.
Yes, -5. So, we know that the torque here is 5 penny centimeter. Dia centimeter ni. Okay, ni kita ambil 1 centimeter, 2 centimeter. 5 penny centimeter. Okay. How about this one? Berapa summation of torque kita ada dekat bahagian kedua? Berapa? Sebenarnya kamu boleh selesaikan terus ni. Okay. Now, kita dah tahu yang torque yang kita ada ialah 5 penny. Okay, here. Dekat sebelah sini kita ada 1 je. So, to make thing equal, Okay, to make thing equal, berapa kita kena tambah dia? Okay. So dekat sini kita ada 5 penny centimeter. Kat sini kita ada berapa? Still pergerakan penny ke bawah. Tapi this one is to the right. 3. Okay, so kita ada 5 minus 3 equals to 2 penny centimeter. Okay, positive 2. So from this positive 2, we know that berat penny is 1p. 1 kali berapa dapat 2?
2.
Kali dengan 2. Positif ke negatif?
Negatif.
Positif lah. Kita nak positif 2.
Yes.
Positif lah. So we know that we need to add up 1 penny dekat positif 2. Here. Tambah 1 penny lagi. These two can equalize the system. Okay, now let's try. Okay, so kita ambil kiri dan kanan. So we have FD equals to FD. FD left, FD right. Pun boleh. Ataupun kita nak buat macam ni pun boleh. Cuba kita tambahkan sistem. FD left. F ialah negatif 1, D ialah negatif 5. Equals to F dekat sini kita ada 2. F yang pertama negatif 1 plus plus pula darab. Darab 2 campur negatif 1 darab 3. So we have 5 here. We have tolak 2 tolak 3. So kita ada 5 sama dengan negatif 5. Equal tak? Is it equal? Left and right? Equal ke tidak?
Yes.
Equal. Okay. Lagi satu cara. Summation of torques within the system. Kita ada negatif 1 kali dengan, sebelum saya letak negatif-negatif ni, saya keluarkan semua sekali dulu. Okay. Ini kita panggil dia kompleks 1, kompleks 2, kompleks 3. So we have FD1 plus FD2 plus FD3. Okay, FD1 kita ada negatif 1, 5 campur FD2 1, 2 campur 1. Kejap ada kotak, kejap tak ada. Kamu ni. 3. Okay, berapa kita ada? Kita ada 5 campur dengan negatif 2 campur dengan negatif 3. So we end up with 5 minus 2 minus 3 equals to 0. Which prove that the system is equal. The system is equal and it is a balanced system. Okay. Okey kah kamu di situ? Enggak okey? Okey? Enggak okey? Kalau okey, kita masuk kepada yang ketiga. Sekejap center of gravity. Okay. Center of gravity. Okay, sampai sini okey?
Okay, sir.
Alright. Okay, next case is about center of gravity. Let's say kita ambil pembaris juga. Okay. Lepas tu kita ada 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Dan 10, 11. Okay. Siapalah pula pagi-pagi ni. Okay. So kita ada, we'll take the same thing. Penny here, penny there. 3, 4, 5, 6. Okay. Kita ada 6 penny. Sama berat penny, distributed sama. Ni kamu bayangkan jarak dia sama lah ni walaupun lukisan dia tak sama. Okay, sama. Sama penny, sama jarak. Okay. 1 penny, 1 penny, 1 penny, 1 penny, 1 penny, 1 penny. Okay. Now, my question is, based on this diagram, where is the center of gravity? Macam sekarang kan dia duduk scattered around kan. Kita nak tahu center of gravity, meaning that at one point here, if we stack all the coin, it will balance out. It will make the things balance. So itu adalah center of gravity, because when we define center of gravity, it is actually a point where all masses being distributed equally. Contoh macam manusia dekat pusat kan, where imaginary, if we weight that point, okay, if we segregate our body towards that point, all body part is going to be equal in term of mass. Inilah cerita center of gravity. Jadi sekarang dia terpecah. Kita nak stackkan all of this penny at one point and it will be equal in term of top, in term of system. Okay. To solve this, we are going to consult with this equation. Okay. Tadi kita ada top equals to FD. Okay. And then summation of top equals to summation of FD lah. Berapa banyak FD yang ada. Kalau kita nak the system balance, we need to always remember equals to 0. Maksudnya summation ni sama dengan kosong. Okay. To solve this equation, to solve this problem, to find out the middle point of weak distribution, we are going to use this equation. Okay. Summation of top, we know this equals to summation of FD. Okay. Ini sama juga dengan weight kali dengan radius. Tadi saya dah beritahu radius tu juga distance. And weight is another form of force. Okay. So now, apa yang kita akan buat, we are going to find the center of it by using this equation. Ini kita namakan, okay, this is the first part of the equation. This is the second part of the equation. And the third part of the equation is summation of W and R. Third part. Okay, beza dia. Tengok baik-baik. The difference is, second part is summation of weight time dengan radius. Means weight here, radius. Okay, this is the radius. Weight here, this is the radius. Weight here, this is the radius. All the way. Tapi untuk the third part is the summation of weight. All the weight and only one radius. And this radius representing the middle of it. Okay, it represent the middle of it. Okay. Sampai situ boleh faham? Beza tempat. Okay. This is summation of top. Ni. WR ni sama je dengan FD. Sama. W is Newton. R is distance. Same as this. Jadi kalau yang ini maksudnya, this is summation of force. And the D will be outside. This is equals. Okay. Jangan terperanjat Ada dua benda ni. Kadang-kadang nampak, kenapa tadi W sekarang F? It is the same thing. W is weight. Weight is force. This distance. R is radius. Radius is distance. It is the same thing. Some books put it as this one. Some books put it as this one. The same things. Different shape. That's all. Okay. So how we want to find the second part? When we try to make the thing equals, the first part is always equals to 0. Ni. Okay. Second part, summation of all the torque we have in the system. Jadi dia akan bergerak ke mana kalau macam dalam ini kan? Dia akan bergerak dekat, kita akan mula dekat satu arah, which is here. This will serve as the axis. Okay. So, kita ada berapa ni? Kita ada penny satu, kita namakan A, B, C, D, E, F. Okay. So, for second part, it will be, okay, F, A, kali dengan F moment arm A plus FB kali dengan F moment arm B plus all the way until FF kali dengan F moment arm F. Jadi kita ada berapa? Kita ada 1 penny kali 1. Okey, itu yang pertama. Lepas tu kita tambah apa lagi? Tambah ini pula. 1 penny kali berapa? Kita kena kali berapa? Berapa dia punya moment arm? Kali
3.
3. Okay. And then kita tambah 1 penny kali
5.
5. Okay. Tambah 1 kali 7. Tambah 1 kali 9. Tambah 1 kali 11. Okay, berapa kita ada? 1 plus 3 plus 5 plus 7 plus 9 plus 11. 20, 36. 36 penny centimeter. This is the whole system. Number 2. Okay. Summation of all torques. Okay, sampai situ dulu. Okay. Ni number 2 second part. Are you okay with this? Jangan. Nanti saya patah balik. Part 1, summation of torque equals to 0. Part 2, summation of torque of the systems equals to 36 penny per centimeter. Now we go to part 3. Okay. Siapa yang belum habis salin ni? Kalau dah settle bagi tahu. Kita nak masuk yang 3 ni. Summation of weight of force and then R. We try to find out the new R. Okay. So second part of the equation say that along the system, the weight being distributed as 36 penny per centimeter. Jadi itu yang kita dah tahu. And now we try to find out if we want to stack all the penny or if we want to sum up all, we try to find out which place, if we put all the penny, the system will be unequal, meaning that it will stable. It will maintain the stability. Tak switch to the, tak skewed to the right, tak skewed to the left. Itu maksud center of gravity, where it is actually the center of the mass. Macam sekarang mass being distributed. Kalau kita sekalikan, where is the place? Okay, to solve that, we are going to use the third part of the equation. Okay, which is summation of force time with D. Jadi berapa banyak summation of force? Berapa banyak penny kita ada? 1, 2, 3, 4, 5, 6. Jadi equation dia is something like this. It will be penny 1 plus, penny 1 plus force 1, force 2, force 3. Okay. Force 1 plus force 2 plus force 3. Okay, saya pakai apa? ABC. Sorry again. It will be force A, force B, force C. A, B, C, D, E, F, D. Jadi kita ada apa? 1, 1, 1, 1, 1, 1. We end up 6 penny D. Okay. Now, in order to make things equal, kita dah tahu tadi, ET akan sama dengan EFD akan sama dengan EF dalam kurungan D. So, ET kita nak kosong. EFD kita ada 36 penny per centimeter. And the third equation, kita ada 6 penny D. So, if we want to find out the left one, we end up dengan this part of equation. 36 penny per centimeter equals to 6 penny D. Automatically, if you want to find the D, it will be 36 penny per centimeter over 6 penny. 6, 36, 6. So, D equals to 6 centimeter. Meaning that the center of the system is here if we put all the penny at one single stack. Ambil 66, letak dekat 6 cm, it will equalize the system. The penny will not switch to the left. The penny will not switch to the right. It will be equal. And this is the concept of center of gravity. Jadi ingat ni formula ni. Okay, nak cari center of gravity. Center of gravity. Okay, start with torque equals to summation of force and distance throughout the system. And it need to be summation of force and the new complex. This is the center, the location of center. Okay, this is the summation of all body weight within the system. Within the system. This is summation of all torque occurs within the system. Ni adalah formula dia. So sometimes you are going to see formula like this. Summation of weight kali dengan radius equals to summation of weight kali dengan radius. This is the same thing. Okay, it talks about the same things. Cuma tadi kita cerita duit shilling. Kalau kita cerita manusia, so you need to know every single segment weight. Berapa tangan dia berat, berapa kaki dia berat, berapa dada dia berat, berapa abdomen dia berat, berapa kepala dia berat, and summate all of sum of all those, you can find out the new D. Kat mana sebenarnya duduk dia punya pusat. Okay, and in real life, when we talk about center of gravity in human, it is not a specific region. It depends on the movement. If you stand still, the COG will be in your body. Pusat lah selalunya. But if you are in motion, sometimes the COG will be placed out of the body. Kat luar badan kita. Okay. So, yang itu lain lah. Ni semua asas untuk cari center of gravity is by consulting this equation. Okay. The equalize of torque within all of the region inside our body. Okay. So, that's all for torque and center of gravity. Ada soalan dulu tak? Okay, semua dah ada?
Ada sir.
Alright. Kita sambung sikit lah. Okay. So, this topic is about angular kinematic. Do you still remember linear kinematics? Benda yang kita belajar awal-awal itu, kita ada displacement, velocity, acceleration. Do you still remember that? Weh, senyap Halo, hidup ya? Ingat tak ni, benda yang kita belajar pada minggu ke berapa ni? Jangan kata tak ada. Lipat korang satu-satu ni. Ni. Minggu ketiga, linear kinematics. Do you still remember this thing? We talks about this thing. We talk about benda ni. Kita cerita displacement versus distance. Do you still remember this? Ni yang track 400 meter. Kalau orang lari sampai sini 100 meter. Kalau orang lari sampai sini distance 200 tapi displacement is the straight line. Kalau orang lari sampai sini distance 300, this is the displacement. Kalau orang lari sampai habis distance 400, displacement dia kosong. Do you still remember this?
Yes, sir.
Ingat tak ingat?
Ingat, sir.
Ingat. Okay. Hari ni we talk about the same thing. We talk about displacement, we talk about velocity. Okay, velocity is v equals to displacement over time. We talk about acceleration. The same thing. Equals to A equals to V2 minus V1 over T2 minus T1. Okay. Ini linear. In angular, we also have the same properties. Kita ada displacement, kita ada distance, kita ada velocity, kita ada acceleration. Same things. Only that in linear, okay, distance being measured in term of meter. Jarak antara point A ke point B, meter. Okay. Velocity in term of meter per second. And acceleration in term of meter per second square. Semua dalam meter. Tapi untuk angular, it is not in meter. Okay, first we need to know what is angular, motion. Motion in angular. Okay, motion in angular is motion of this. Apa ni? Pergerakan bagaimana ini? What kind of movement is this one? Rotational. Pergerakan begini. It start from point A, dia bergerak ke point B. Katalah sampai sini. Bergerak ke point C. Bergerak ke point D. Bergerak ke point E. And eventually become A again. It rotate. And when we talk about angular, you need to have the same thing as what we have in torque. Axis of rotation. So movement around the axis of rotation is angular movement. Okay, movement around the axis of rotation is angular movement. So in linear, it is being measured in terms of meter, but since it is rotational, katalah kita ambil A ke B ni kan, since it is rotational, the distance is not in meter anymore. Kalau kita measure radius ni, this is what we call radius in between two segment. We can measure it in meter. Bila kita measure in meter, ini linear ke angular? Is it a linear motion or angular motion? Meter.
Yeah.
Linear. To be exact, curvilinear ke rectilinear kat sini? Curvilinear. Ini linear. Tapi kalau kita nak ukur in term of angular, berapa jauh pergerakan antara A and to B in term of angular, we are going to measure benda dekat sini. Means we are going to measure the first one, distance, okay, in meter, but in angular, distance between A and B being described in term of degree. Berapa degree dia bergerak? That is the distance. Or, to be exact, in angular, it is known as, this one, buat kosong, belah 2. Nama dia, pi. Okay, how much pi is how much distance. So, distance is pi. Okay, and it being measured in term of sini meter, sini degree. Okay. Contohlah kita ambil muka jam kan, we tick clock face. Daripada pukul 12 ke pukul 3, berapa jarak dia? In term of angular. How much distance for this movement? Berapa?
Degree.
Hah?
90.
Okay, 90 degree. So the pi is 90 degree. Okay, kalau dia teruskan perjalanan ke pukul 6, berapa jarak baru dia?
180.
180. Okay, and then continue satu lagi. Dia jadi berapa?
170.
Kalau kita teruskan sampai habis, dia jadi 360 degree. Kalau dia pusing 2 kali, berapa jarak yang dia cover? 1, 2. How much distance covered angularly? It will be 720 degree. So, in angular, the first one, the basic one, distance being measured in terms of degree, and it is called as pi. Distance. Kawan dia, if in linear we have distance, the kawan of distance is displacement, which is the shortest way from point A to point B. Dalam angular, it also has displacement. Benda sama tapi dia sengit. And this is known as theta. Okay. Theta dalam unit sama. Degree. Pasal this is distance, this is displacement. This is distance, meter. Displacement pun dalam meter. Okay. Now, kalau dia bergerak daripada pukul 12 sampai pukul 3, what is the theta? What is the displacement? From 12 to 3. Berapa displacement dia?
90.
90. Okay, 90. Positif ke negatif? Think carefully. Is it positive or is it negative? Come on. Kak Alip Mon. Come on. Positif ke negatif? Tak payah sakit kepala. Pergerakan ni ke mana? Pergerakan ni ke mana? Negatif, yes. Pasal pergerakan ni ke mana? Ke
Bawah.
bawah. Clockwise, negatif. Okay. Alright. Daripada 3 ke, katalah daripada 12 ke 6, berapa theta dia? Negatif 180. Okay, sekarang katalah jarum 12 ni dah sampai 9. Okay, now what is the displacement? What is this displacement? Fikir betul-betul. Displacement is the shortest. 90 degree. Ni displacement ni nampak. Jarak paling pendek. Dia tak boleh lah cut macam ni. Dia kena ikut rotation. But, kalau dia dekat sini, okay, this is the shortest way. Tapi kalau dia dekat 9, dia bukan macam ni lagi dah. It will be this way. So, 90 degree ke sini. Okay. Mana. Alright. Okay, ni distance and displacement lah. Okay, so in angular, it can be described in term of degree. Kita ada pi, kita ada theta. These two thing is actually the same thing. Kadang-kadang kamu tertulis theta untuk pi, I'm not going to penalize you for that because these two things actually the same. Sama macam ni, distance and displacement. It is both in meter. Okay, next one. In angular, unit. Okay, unit in angular. The most common unit is degree. Okay, degree. Other than this degree, kita juga, okay, whenever you answer any angular case, you need to report the answer both in degree and in radian. Okay, dalam radian. Okay. Jadi, one full rotation equals to 360 degree, or it will be 2 pi radian. Okay. This radian, how much is a radian? So, 1 radian equals to 57.3 degree. Okay, why 57.3? You may find this in YouTube. Carilah, dia ada penerangan banyak. Okay, cuma in a simple way, why 57.3? Okay, when you do any circle at 57.3, ni kan yang kita namakan dia sebagai radius ni. Radius. Ini, jejari ni is also radius. So at this 57.3, if you measure linearly, okay, this 3 pi, all this radius, it will give you the same value. Kalau value sini x, value sini confirm lah x. This radius also going to be x at this particular angle. And this is 1 radian. Okay, this is 1 radian. Kamu cek kat YouTube, dia akan bagi kamu penerangan. Dia akan buat sampailah kamu boleh dapat sehalus mungkin and everything is equalized at this particular angle or at this particular theta. Okay, jadi dalam angular, the unit will be degree and radian. Okay, other than this, you are going to see revolution. Okay, 1 revolution equals to 360 degree, or scarcely, jarang-jarang kamu akan nampak rotation. Benda paling simple ni kita jangan nampak. We are going to see a lot in term of these two. So in any angular case, please report your answer both in degree and in radian. Okay, macam mana nak report dua tu? Katalah jawapan kamu, angle yang kamu dapat ialah 340 degree. So you need to change this degree to radian. Okay, how to change degree to radian is by degree divide with 360. Dapatlah, divide 360 pula. Divide 57.3. Dapatlah jawapan dalam radian. If your answer is in radian, you need to change that into degree. Apa yang kamu kena buat ialah that radian times with 57.3. You're going to end up dengan jawapan dalam degree. Ni rule of thumb. Please remember this. Any angular case being answered in either degree or radian only, you are not going to get full mark. So you need to have both of the answer. Ni unit dia. Unit. Kalau dalam linear, unit dia senang, meter. Dalam angular, degree of radian. Okay. And then we have two type of angle. Okay. One is known as absolute. Second one is known as relative. Okay. You are going to use these two. So what is absolute and relative? Alright. If your angle of interest located in between body parts, macam ni, kita nak ambil angle ni. So it is an intersection between your thigh and your lower leg. Ni betul. This kind of angle is known as relative angle. Katalah kita nak tengok flexion elbow. So antara kita punya humerus dengan kita punya forearm, we have our elbow. This is relative. How about we want to find out bending of our vertebra? Macam ni kita nak tengok vertebra kita ni sengit berapa degree. We don't have any other bones intersect with our vertebra. If that is the case, you are going to use second type of angle, which is known as absolute angle. Angular orientation of a body segment with respect to a fixed line of reference. Reference line are usually vertical or horizontal. Okay, so we need to come up with one reference line, line yang kita akan buat imaginary. And this line need to intersect with the bone parts that you have interest on. And this line is only applicable if, okay, if kamu boleh guna yang lain ni if there are no other intersection between bones and bones. Kalau kata nak buat rotation at the hip, ada tak bone yang attach dengan hip kita? Ada tak? Kita nak tengok berapa banyak kita boleh rotate dekat hip ni. Do we have any bone attached to hip? Kat sini. Ada tak dia? Hello. Okay, come on. Kamu masih ada di situ ke tidak ada? Hello, hello. Anybody home? Hello class. Anybody home?
Ada sir.
Ada. Okay. Kalau kita nak buat dekat hip, are we going to use absolute angle ataupun relative angle?
Absolute sir.
Kenapa? Kenapa hip kena pakai absolute, not relative? Because there is no any other bone intersect. Selagi ada tulang macam ni kita nak buat pelatang dengan dorsiflexion, we can use our lower leg as the reference. But if the angle does not have any reference, we need to come up with reference line. And when you do so, this is an absolute angle. Tu je beza absolute dengan relative. Okay, ni contoh tadilah radius ni. Okay. Alright. So let's go to some of the properties. Between two bones. Imaginary fixed line, either horizontal or vertical, intersect with the bone in interest. Okay, alright. So let's go to the first part. Okay, the first properties of angular kinematics is displacement. Okay, displacement dengan distance. Alright. So I'm going to put it as both angular and linear. Okay, in linear, distance being measured along the pathway and it being described in meter. However, for displacement, it is actually the straight line between start and end, also being measured in meter. In angular, since the motion is a rotation, okay, distance or the name of pi being measured in degree, or in term of theta being measured also in term of degree. Ni angular. Okay, berapa darjah, that is distance. So if let's say the object start from A and rotate 10 times, 2, 3, 4, 5, 6, 7, 8, 9, 10. The question is how far that object rotate. It refer to angular distance. So 10 kali, the angular distance going to be 360 times 10, which end up 3600 degree. Or in radian, it will be 3600 divided with 57.3. 62.83 radian. So you need to come up with these two equation, these two answer. Ini paling mudah. Distance. Okay. Next one is angular velocity. Okay. So in linear velocity, okay, velocity equals to displacement over time, where it will be recorded in unit of meter per second. So in angular velocity, okay, the symbol will be something like this, macam W bulat. Okay, this is known as omega. Okay, this is omega. Omega representing velocity for angular. So linear velocity displacement over time, omega is the same thing. But here is displacement. In angular, it is theta. Time lah. Theta over time. Sama je. Okay. Ataupun sekejap saya tulis. Theta. Theta over time. Ataupun symbol dia will be theta over time. And the unit will be degree per second. N. Radian per second. Atau can be degree per second, radian per second. Ini pun sama, meter per second. Ini unit dia. Okay, the same thing. Okay, the same thing. Okay, contoh. Katalah kita ada jarum ni tadi kan. We have the jarum jam. Okay. What is the velocity of the watch from 12 to 3? Berapa velocity dia? Omega equals to theta over time. Okay, berapa theta dia? What is the theta for this omega? 90. Okay, time dia berapa? Time kena second. This one is 15 minutes. So 15 minutes times 60. Berapa dapat? 0, 3, 9. 65, 03, 900 second. So 90 over 900. We have 1 over 10. We have 0.1 degree per second. Berapa radian? Berapa radian dia? 0.1 degree sama dengan berapa radian? 1 radian 57.3. Kalau 0.1 bagilah 57.3. Tu 0.0001 radian per second. Ni velocity dia. This is angular velocity dia, omega dia. Ni cara penggunaan lah. Okay, this is how we use omega. Katalah kalau kita ini jarum minit, how about jarum saat? Okay, this is jarum minit. How about the velocity for jarum saat? Sama, 90. Berapa saat? Between 12 to 3? How many second? Ni tadi kita pakai jarum minit. 15 minit. Kalau jarum saat, berapa second? Between 12 to 3. It will be 15 second. So, what is the angular velocity of it? 6 degree per second. Ataupun 6 bagi 57.3, we have 0.1 radian per second. Okay, inilah kelajuannya. Okay, this is velocity. Okay, kalau kata linear tadi, V equals to displacement over time. meter per second. But in angular, it will be degree and radian per second. Okay, sampai sini dulu. Are you okay with it? Okay kah? Enggak okay kah?
Okay, sir.
Okay.
Okay, sir.
Alright.
Okay, sir.
Okay, kita pergi ke properties terakhir sebelum kita stop. Angular acceleration. Right. So angular acceleration in linear, we have acceleration equals to velocity final minus velocity initial over time final minus time initial. Ataupun it can be velocity over change of time. Sama juga dengan yang ini. Cuma dekat dalam angular acceleration, the unit will be alpha. Sama je A dia ada echo je. Point ni tau. Ni tak ada echo, ni ada echo. Point. Equals to velocity. Okay, velocity dekat dalam angular tadi apa? Omega. Jadi dia samalah. It will be omega 2, omega final minus omega initial over the change of time. It is the same thing. And the unit will be degree per second square ataupun radian per second square. Or it can be written as degree darab second negatif 2 radian darab second negatif 2. Okay. So, penggunaan dia. Okay, penggunaan dia. Let's say kita ada manusia yang cuba menghayun tangan dia. Okay, dia cuba menghayun tangan dia. Okay. So, at starting position, the velocity is 0 and at an instant of releasing the bowling ball, the velocity of the hand is, let's say, 180 degree per second. And this action occurs in 1.5 seconds. So, what is the acceleration of the hand? Ini angular acceleration. Acceleration at the shoulder. Berapa laju shoulder dia rotate. Bolehlah cari acceleration tu. Equals to omega 2 minus omega 1 over change of time. Omega 2 is 180 degree minus dengan omega 1 0 over 1.5. Dapatlah. Berapa kita dapat? 180 bahagi 1.5. 1.5. Kita dapat 120 degree per second square. Berapa laju 120 degree per second square ni in term of radian? Bahagilah dengan 57.3 convert. Or equals to 2.09. Is it? 2.09 radian per second square. Ni adalah kelajuan hayunan dia tadi. This is how we explain things in term of angular. So linear and angular case is actually the same case, except unit dia tak sama. Except linear we measure in term of straight line, angular we measure in term of rotation. That is the difference. Other than that, it's actually the same thing. Okay, so we are going to stop here. There are several other properties in kinematics that we are going to continue next week. Okay, and then towards the end of next week class, kita akan tengok relation between linear and angular. Contoh kita ada distance tadi kan, kita ada distance. Kalau angular, okay, sama dengan r pi. Velocity sama dengan r omega, and acceleration sama dengan r alpha. Beza dia ada ni je. This is how we relate linear and angular. We include radius. Okay, saya bagi hint dulu. Contohlah kita sepak bola kan, we try to kick a ball, the ball travel. How fast the leg movement means how fast rotation occurs at the hip. This one is angular cases. How fast the ball goes, this is linear cases. Kalau kita cari omega dekat sini, kita boleh jumpa velocity dekat sini. This is what you need to have in your analysis later on. The relationship between linear and angular cases. And this we are going to discuss this one next week, next class. So I need you to do this. Okay. Please read this topic. Please read this chapter. So dia akan cerita angular displacement, angular apa semua ni balik. Please read this one. And next week, it will be much easier for you to understand how to find the relation between those two things. Okay, ni benda-benda relationship dia. Alright.